So this is damage stability continued, and the lost buoyancy method, there is no change of displacement. The important factors then one should keep in mind that there is no change in displacement, but in added weight method there is always a change in displacement. So actually the name comes from this addition of weight, that is the water that has flooded the hull is treated as an added weight. So added weight, there is change of displacement. And as a result of this change of displacement, you have change in width, change in CG of the ship, that is with change of kg of the ship. So this is the important point which one should remember. And another point that is more important, so this is number one and this is number two, and the third point is that although you will find that your GM is different in the, you can calculate the GM and GM will come out to be different in the two conditions, but the ultimate writing moment with which we are concerned, so this writing moment calculated from lost buoyancy and added weight method. Is the same. So this has to be kept in mind, is to be noted. So you want to check the final condition of the ship, and it is done by the two methods, although you will get different values of GM and GZ, but your ultimate writing moment has to be the same. So what happens, the GM you can calculate if you want, say GM is calculation of GM by lost, say GM1 is calculation by lost buoyancy method. And GM2 is the GM that has been obtained by from added weight method. Then you will find the two writing moments, since the two writing moments are to be the same, you have displacement multiplied by GM1 is equals to, say I give displacement, the virtual displacement in the added weight method multiplied by its GM, GM calculated is different. So this GM2 will be equal to delta divided by delta V multiplied by GM1. So delta V is displacement, or you can call virtual displacement Why this is called virtual is because the water that has gone inside the ship, although we are treating that as a addition to the weight, but actually it has communication with the outside sea. So that is why we are saying that this is a virtual addition. So this is going to be a virtual displacement. Displacement in added weight method. So this one should remember that the writing moment is to be the same in both the cases, in both the types of calculation, that is lost buoyancy and added weight, and although the GM calculation is going to be different. So one should not leave the calculation after calculation of GM, that is either in lost buoyancy or added weight, but if one wants to go the whole calculation, then it is always better to multiply it by the relevant displacement and get the writing moment. Now this can be plotted as the writing moment versus your angle of heel. So this is the curve that one will get. Your final, this is would be your displacement multiplied by GZ, and on the horizontal axis will be your theta, that is your angle of heel. So this curve is more important than just GZ versus your heel curve. Now coming to the calculation of this lost buoyancy, calculation of damaged draft. Using lost buoyancy method. Now, before we start, let us give some, let us state what are the parameters, that is more important. Say, from here, let me this as 1. Let us keep, say, V to be the molded volume of flooded compartment. Below waterline WL. Now the figure that I have already drawn, that means with reference to this figure. So this was my figure. So the original waterline was WL. Now the molded volume is this volume. That means the total volume keeping the intact buoyancy component. This is the total volume. So this is the molded volume. Now V prime is the net lost buoyancy. Below WL. Sorry. So this V prime has to be calculated from V, and we will do that. Another thing that is important is the permeability of the compartment. Permeability is the volume of the compartment which can be occupied by flood water divided by the total volume. So, that is the permeability. So, different compartments have different permeabilities according to the type of cargo and the nature of the space. Now, P is total mass of liquid. In breached tanks. Before damage. So, this has to be subtracted. And rho is the density of liquid in breached tanks. Breached is ruptured tanks. This is given in tons per meter cube. Mu s, of course, uh, we can calculate with mu s, but if we don't have any figure for mu s, you can take it as 1. So, mu s is called surface permeability. So, you take mu s equal to 1 if data not given. So, that means the amount of water plane area that can be taken up by the water. Third one is A is your original water plane area or area of water plane WL. And A is your area of portion of water plane WL within compartment limits. So, if you refer to this figure, so that means A is the total water plane area at WL and small a is this area of the compartment, that is within the compartment bulkheads, within the compartment boundaries. Now, next is A prime. Now, A prime is net area of water plane and is actually a very important parameter for calculating your sinkage as well as trim. So, A prime is the net area of water plane WL. This we should remember, remaining intact after flooding. Now this is the intact area of water plane of subtracting your flooded portion. So this will be how much? This will be A minus mu s multiplied by small a. So this is the net area of water plane W remaining intact after flooding. So now let us calculate the sinkage, or sometimes in naval architecture practice we call this as parallel sinkage. That means we assume that the ship is not having any trim at this stage. So if you want to calculate the final draft of the ship, first assume the ship has sunk to a waterline parallel draft of say WL1, and then it has trimmed, it has rotated on about this longitudinal center of flotation, and the final waterline is WL2. So two calculations, that is your sinkage and trim, are superimposed or combined, that is numerically they are added, and we get the final result or final draft of the ship. Now, so how much is going to be the parallel sinkage? So parallel sinkage will be V prime over A prime. So V prime is your the amount of flood water that has entered, and by lost buoyancy method. So this is the amount of water that has entered, and the amount of water that has you have gained in buoyancy. So I told you the buoyancy that has been lost is to be made equal to the buoyancy that has been gained by the ship sinking at a draft WL1. So this shaded portion is equal to your lost buoyancy. So this is the volume that you have lost in buoyancy, and this portion is the buoyancy that has been gained by this layer as a result of sinking from draft WL to WL1. So buoyancy lost is equal to buoyancy gained by the sinkage. So here we make this parallel sinkage is you simply distribute this volume, the V prime, over the damaged water plane area. You should not take the total water plane area, but the damaged water, that is the total water plane area minus the portion that has been flooded. So you simply divide by that and you will get the parallel sinkage. So this will be equal to, so V prime is my lost buoyancy. Now this is equal to the V that I have already said is your molded volume. So molded volume of flooded compartment minus your any intact buoyancy in the region. Intact, or rather you can write intact volume. Now in this sphere, you can look into this diagram. For simplicity, I have just drawn say a tank top, and this volume say has not been flooded. Say in blue, this much volume is the intact volume within this compartment. So the total volume V minus this intact volume, and also take away, so this multiplied by the permeability minus your minus P is the water that is already been inside the tank divided by the density of water in the tank. So that means any water that is remaining within this space should be subtracted. So we are simply concerned with the amount of water which has flooded the compartment of the up to waterline WL. We are not to consider any water that is already inside the compartment. It may be by accident or whatever it is, it can be there, and also you have to leave out the intact portion of the volume inside the compartment which has not been flooded. So, this divided by the A prime is your A minus mu s multiplied by A. So, that is your parallel sinkage. Now, what happens is that if you look now, the ship is not a rectangular box. You will find that if it is a forward compartment, that the say the breadth of the compartment at WL will be somewhat less than your breadth at WL1 because of the curvature of the side shell. Because of the curvature of the side shell, of course, for this layer of sinkage is, you can see it is not in meters. This can be quite small, but if you want to take the two water plane damaged portion of the water planes, then you can make a average. So, you can write for more accuracy, one can write sinkage will be equal to V prime divided by A prime plus A1 prime divided by 2. So, I take the average areas, that is the remaining areas, because of the curvature of the hull and the hull not being a rectangular box. So, this A prime is the intact portion of the water plane. Remember, when I write A prime, it means the remaining portion of the water plane which has not been flooded. That means this one and this one, leaving out this one, the damaged portion. And A1, A prime refers to waterline WL. So, in fact, this is 0. So, I have not put any subscript, and A1 prime refers to waterline 1. So, that is the, in order to do this calculation. So, this one can write. So, A1 prime is your equal to A1 minus mu s A1. This 1 always, subscript 1 always refers to waterline 1. So, that is after the parallel sinkage, the waterline, this waterline W1 is referred to as 1. And this A1 similarly is area is impaired water plane. Again WL1 within the damaged compartment, within the compartment. Now, you make this replace these areas by their TPC values. Now, TPC, or what is called the tons per centimeter of immersion, that is equal to area of water plane area in normal, in any ship. If you want to calculate the TPC, or I am writing is, this is called tons per centimeter of immersion. So the formula is, this is calculated from the water plane area. So TPC is area of water plane, this multiplied by 1 by 100 and multiplied by the density of the water. So first you calculate 1 by 100 is 1 centimeter, there is 1 by 100 centimeter, and AW is given in meter. So that is why AW 1 by 100 multiplied by rho. So from here you can calculate your water plane area. So this A prime will be how much? So A prime I can write, this is equals to 100 divided by rho into TPC prime. Prime means your calculation is based on the intact portion of the water plane, and A1 prime is again 100 divided by rho TPC1 prime. So this for waterline, this is at WL, this is evaluated at WL1. So A prime plus A1 prime will be how much? This is 100 by rho multiplied by TPC prime plus TPC1 prime. So now calculate sinkage. This TPC prime and TPC1 prime, they always refer to intact portion of water plane areas. Intact portion is, again, I am just telling this again, such that this is your intact portion. This one, this one. You leave out this damaged compartment. So sinkage is, in terms of TPC, we have to calculate. So this will be 2V prime divided by A prime plus A1 prime. This is equals to so ultimately you will get so we have finally calculated your sinkage. Now how you are going to calculate this TPC prime and TPC1 prime? Of course, you have to calculate from the water plane areas. So this is your sinkage, or sometimes this is also called parallel sinkage. So this one you can TPC prime and TPC1 prime you can calculate from hydrostatics from the water plane areas, subtracting the compartment water plane areas. You can calculate from the hydrostatics. Normally it is given in terms of water plane area coefficient CW. So CW multiplied by your rectangle and the water plane, that will give you the water plane area. So this you can normally can be calculated from ship hydrostatics. Now the next item that we have to calculate. So we have calculated the parallel sinkage, that is the distance between, or the vertical distance between WL and WL1. So now after this we have to calculate the trim. Now trim, as you know, trim always occurs, that is the moment about a LCF, or a center of flotation. So this is our next step. Now before we do this, we have to calculate the trimming moment. This trimming moment caused by flood water. So that means the buoyancy at that particular location has been absent or has been taken away. So that has created some kind of a trimming moment in the ship. So if you had sufficient buoyancy in this region, then the ship would not go down, isn't it? Ship would have been floating at the original water line, but the ship is sinking because there is inadequate buoyancy in this compartment. So there is a loss of moment or trimming moment. So now this is caused by, say, the amount of flood water multiplied by rho multiplied by x. Now x is the distance between the center of buoyancy of the flood water and the center of this parallel, say, parallel water plane, parallel sinkage. So this normally you can just have a rough guess. So this, if I call this as center of flotation at this region, say this is F1 prime, and center of flotation of the water line, say this is F. Sorry, this is F prime of the damaged portion is F prime. Then your center of buoyancy will be located somewhere here. It is midway between F1 prime and F prime, say somewhere here. And X is your moment lever, so that will be from the center of buoyancy of the lost volume. You calculate to this region, so this is will be your X. So you always calculate the transfer of moment. So here the moment has been transferred from the center of this volume to the center of the added gained buoyancy. Center of lost buoyancy to center of gain in buoyancy. So the distance between these two centers is given by x. So that is your moment lever. So this is the moment causing trim, that is v prime rho into x. Now the next problem, that now how to calculate this. Of course, we can we have got the value of V prime. Rho is the density of the flood water, and x, of course, we can calculate. You should remember that x lies midway between f prime and f1 prime. X distance between center of flooded volume to middle of f1 prime, f prime. Now calculate, if you want to calculate the trim, one has to calculate moment to change trim. Moment to change trim per centimeter, if one remembers the hydrostatic calculation which you have been taught, then this is given by a formula called displacement multiplied by BML, or sometimes instead of BML you can put GML divided by 100 into L. So that is the formula for moment to change trim, which is derived from the writing moment in the trimmed condition, that is displacement into GM theta, that comes from GM writing moment will be this displacement into GM theta. Now this theta you can write as displacement in GM theta, you can write is normally by this x divided, x is the amount of trim divided by L, and GML is replaced by BML. Since GML is very much nearer or almost equal to BML, you can replace GML with BML, and amount of this x is actually 1. So this, if it is 1 meter, it is 1, 1 centimeter it is 1 by 100 of a meter multiplied by L. So this will be displacement multiplied by moment of inertia longitudinal IL divided by B divided by 100L, and this will be simplified into rho IL divided by 100L. So your BML is IL divided by the underwater volume. Now the trim calculation that we are doing at WL1. Say this WL1, we call this say draft T2. Say T2 is the draft at WL1 where we are doing the trim calculation. That is, the ship has sunk to the draft WL1 by parallel sinkage, and then we are giving a longitudinal rotation of the ship, and we are coming to the final water line WL2. So this MCT1 prime you write because it is based on the intact portion of the water plane, not the full water plane area. So this will be rho IL1 prime divided by 100L, where L is the length of the ship. So L you can write length of ship, or you can, for all practical purposes, you can take this as LBP. Since the hydrostatic calculations are always done on LBP. So this is our equation. Now the problem that if you want to solve this, then we have to find out what is the value of the longitudinal moment of inertia. So we have to calculate IL1 prime. So this is the longitudinal moment of inertia of intact portion of water plane. At WL1. I think this is and now this has to be calculated from the undamaged water plane moment of inertia. So IL1 you write, so prime indicates the intact portion at WL1, and you calculate IL1 from IL1, which is the longitudinal moment of inertia of undamaged water plane WL1. This normally you can get from hydrostatics, or you can calculate. So, but this should be your undamaged water plane. Now all this is calculated about its center of flotation. Whenever the hydrostatics is done and moment of inertia are calculated IL1, it is always about the center of flotation, or the CG of the water plane area. It is never calculated about midship. So this IL1 prime, this will be how much? Now this is IL1 is about your F1. Now if you transfer this about midship, this will be IL1 plus A1. Now midship I am writing in this sign, cross circle F1 square. This IL1 I have transferred to midship. So this one should remember that if there is an area, okay, and the CG lies here, then say this is your CG of the area. If I want to calculate about some other axis, your moment of inertia, and this is your D. So then say this axis is XX, then IXX is equal to moment of inertia about CG plus the area into D square. So this is normal in mechanics. This is a fundamental relationship between transfer of the axis. So that I am applying here. So from this equation, now this is your moment of inertia about midship. So from here you subtract the contribution of moment of inertia about the compartment, about the area inside the compartment, or the lost moment of inertia. So that you multiply it by mu s multiplied by A1 into n midship F1 square plus IL1. You follow what I have done? Now this moment of inertia of this water plane, that is about F prime, sorry, not F prime, about F1. F1 has not been indicated here. F1 has not been indicated. Anyway, so this is about F1, that is the whole water plane, okay, including this portion. So because I have written IL1 is the undamaged water plane WL. So this I have transferred from F1 to midship. I have added AD square. I have got this. Now we have to subtract the contribution of moment of inertia from this flooded compartment, or the area between the two bulkheads, compartment bulkheads. So that is given by IL1 is your moment of inertia about the axis, about the middle of the compartment, axis going through the middle of the compartment, and midship, say this is your location of F1 is somewhere here. So midship to F1 is your this distance. So this is your midship F1. So about its own axis, it is IL1. So moment of inertia of this extent of water plane between the two bulkheads, that is its own moment of inertia, is IL1 plus the area is A1, or I should have written it as A since it is at waterline WL. So anyway, this A multiplied by midship F1. So this is your moment of inertia multiplied by the surface permeability mu s. So I have subtracted from the original water plane area the moment of inertia, that which has been contributed by the water plane inside the two compartments. Now you transfer this to the original axis, that is original axis you have to transfer. Oh sorry, this is I have done the calculation with waterline L1. Sorry, this is with waterline L1. Yes, now it's okay. So now you transfer this to the axis which is passing through F1 prime. So this IL1 prime is the moment of inertia about an axis which is passing through F1 prime. Now what I have calculated is the moment of inertia that is passing through the midship. So now if I want to calculate your about F1 prime, which is the CG of the water plane, so you simply subtract AD square. ICG if you want to get, that is IXS minus AD square. So this AD square will be A1 minus mu s A1 multiplied by so this is my damaged moment of inertia at waterline 1. Now in this equation one has to substitute the values of A1 in terms of TPC or tons per centimeter of flotation. And we can keep mu s equal to 1 for simplicity of the calculation. Now, what is the equation for IL? Any longitudinal from moment to change stream, you can derive that. Moment to change stream per centimeter or meter, whatever it is. Per centimeter, it is 100 L divided by rho. This I have already showed you. So from this formula you get IL. IL is equals to mcd per centimeter 100 L divided by rho. So now, and what is the TPC value? TPC in terms of area you write tons per centimeter is equals to A multiplied by 1 over 100 multiplied by rho. So from this we will calculate A is equals to 100 divided by rho multiplied by TPC. This formulas one should remember. These two formulas. Now you calculate this mu s multiplied by A1. So from the above formula, any area, so you simply multiply it by mu s 100 divided by rho. The small a1 you write as TPC1. So that means this is the contribution of the water plane area within the compartment bulkheads. That is, this TPC1 will pertain or will be related to the water plane area within the compartment. Next, what is the moment of inertia mu s multiplied by IL. Now again going back to mechanics, if we take the water plane area inside the damaged compartment to be a rectangle, say this is your rectangle, and one has to calculate the moment of inertia. So there is a simple formula. Say this is your axis. If this is your length of the compartment, you can write this as S, and the normal, if this is the breadth of the compartment, then moment of inertia, in short I am writing as mi, this will be 1/12 b multiplied by s cube. So this is equal to 1/12 bs multiplied by s square, and bs is your area, so this you can write as 1/12 a multiplied by s square. So this you put it here. So this is mu s multiplied by IL. So this will be 1/12 of area A1 multiplied by S square of this portion of the water plane inside the compartment bulkheads or compartment boundaries. Now again you break down this A1 in terms of TPC. how much you will get? So mu s IL will be equal to mu s into 1/12 multiplied by A1 will be again 100 by rho, 100 by rho multiplied by TPC1 multiplied by S square. S to be defined as mean length of lost area. So next we can calculate the midship F1 and we will substitute this and calculate IL1.